Hello, my name is Dr. Peggy Norris, and welcome to the Sanford Underground Research Facility's virtual Neutrino Day. Back when I was in 8th grade, I got fascinated by the idea that matter is made up of things that are too small to see. And that's what I want to talk to you about today. We're going to talk about neutrinos and how small is a neutrino really. Joining me today is our two students that are part of our internship program. You can see them in the photo, but I'd like to introduce them in person. We have Caitlin. Caitlin is an education major at Augustana University. And we have Adrian. She's a chemistry major at Black Hills State University. And they are working here for the summer, mostly virtually, but today we have them in person on site. So I hope that everybody rounded up the things that we had on the website that would make this a chance for you to do a hands-on activity. And we're going to start by looking at something we can barely see, and that's salt. So I hope everybody has salt. If you could find a plate or a table and just put a few grains on there. We are going to look at that very closely. So there's all kinds of different kinds of salt, and here's some examples. So look at it, compare it to the picture on the screen, and try to figure out what kind of salt that you're closest to. And you can see from the picture that salt comes in all different sizes. So I would like you to use a toothpick to separate out a grain or two of salt and see if you can measure it with a ruler. So if you have a magnifying glass, you might want to look through a magnifying glass and see approximately what sizes of salt you see with the ruler. Can you do this, or is the salt too small? We have chat going on, and if you'd like to give your answers to some of these questions in the chat box, that would be great. So I'd like to know approximately what size your salt crystals are, and or are they too small to measure? So I'm going to give you just a minute to do that. All right, once you've tried that, then I'd like you to crush a few grains. You can use the back of a spoon, put your thumb in it so if you've got a plastic spoon so that it doesn't break, and just crush a few grains and then look again. If you have a magnifying glass, look through the magnifying glass, and now can you measure the salt with a ruler? So we have our interns helping to demonstrate this as we go. All right. Sometimes we need to go to more sensitive tools, so maybe our ruler isn't sensitive enough to see the scale of this crushed salt. So we've actually have a little plate here, which you guys don't have, but I can see grains of salt on a scale like a ruler, but each of the lines is 0.1 millimeters. So really much, about a factor of 10 smaller than the smallest line on a ruler. And you can see that this is uncrushed salt here, but you can see that it ranges from really tiny to pretty big flakes. So we have a variety here. Once it's crushed, you'll probably see that it's all tiny. So we could go to even more sensitive tools to look at the salt. And if we used a microscope, which you may have used in school, we can see grains of salt compared to, here's a straight pin and a sewing needle for scale. And this says grains of sodium chloride. That's another word for salt because it's made up of atoms, which we'll talk about in a few minutes, of sodium and of chloride. But you can see on this scale, you see structure in that it's squarish or cubic crystals of salt. So we explore matter at all kinds of scales. And here's just a meter. So a meter would be about like this. And decimeters, the next one down, centimeter, it's about like this. Millimeter, 0.1 millimeter is about the width of a human hair. That's about the limit of what you can see with your eyes. So a microscope will let you go down to smaller scales. And so we're going to do another experiment now. And we're going to see what happens if we take the salt. We're going to take about a teaspoon of salt, and you're going to add it to a cup of water and observe closely what happens as you stir it up. So you might notice some changes. So if you're on a computer right now and you have access, we have a board called a Wonder Board on Google, and you could add one of your observations to that board. And we would love to see you do that. If you don't have access to a computer, you could just put it in the chat box. But what we'd like you to write in either the chat or on the Google board is one observation you noticed when you added the salt to the water. And can you still see the salt? Can you see it with your eyes, or can you see it with a magnifying glass if you have one? So Erin, are there some comments? Oh. Okay. Okay, so we'll move on, but go ahead and record your observations in the chat or on the Jamboard, and we'll look at them at the end of the talk here. All right, so Neutrino Day is all about matter and the mystery of matter, and matter is the stuff all around you. By definition, matter has weight and takes up space. So, do you think that salt is matter? Does it take up space? You had a teaspoon of it, so it took up some volume there. Do you think it has weight? Can you tell by touching it and feeling it? So, do you think salt is matter? So think about that for a minute. And then think about the water. Does water take up space? Does water have weights? So is that matter? And what about when you mix the two together? It appears that the salt disappears, but is it still there? That's one of the mysteries that we can explore when we study the world around us. Matter is made up of atoms, including us. All the normal matter that we can see around our world or in the stars everywhere is made up of atoms. And we can actually calculate how many atoms are in a grain of salt. Scientists can weigh it, and then they know that salt has two kinds of atoms, sodium and chloride, and so they can calculate it. And the answer is a lot. It's 1 with 18 zeros behind it. So that is 1 quintillion atoms. So in science, we use what's called scientific notation, which is a shorthand for really large numbers. So we basically count the number of zeros when we look at big numbers, and we write that in an exponent next to the 10. So a quintillion is 10 followed by 18 zeros. So it's a really, really big number. So that's a lot of atoms in a very small grain of salt. So what have we learned so far? We've learned that atoms are too small to see with your eyes, that a grain of salt that's about 0.1 millimeters in diameter contains a quintillion atoms. So how small is an atom really? It's really, really small. So we can also use scientific notation to go to very small numbers. And when we do that, we use an exponent, but we put a negative sign in it because we're going to go to small numbers instead of large numbers. So it turns out that an atom is about 1 nanometer, or 1 billionth of a meter in size. So we call that 10 to the minus 9, or we call it a nanometer for short. But we can go further because atoms have components, and there's 3 basic parts of an atom. The inner part is the protons and neutrons, and they're contained in the atomic nucleus. And then orbiting around the outside of the atom are electrons. And they really are what define the size of the atoms. So when we talk about how big an atom is, that it's 1 nanometer, we mean that those electrons are orbiting out to about a billionth of a meter away from the center of the atom. But the nucleus itself is even smaller. So here are some numbers, and we're going to use these to model an atom. So an atom is about 1 nanometer, or 10 to the minus 9. And we have a number line on the wall over here. So Caitlin, can you point to the atom on there? Okay, so that's our 10 to the minus 9. So every one of those pages is a factor of 10 bigger or smaller. So we're doing powers of 10. So you can see the atom, and can you also point to the grain of salt? Okay, so that's the 0.1 millimeters, okay? The parts of an atom, the nucleus of an atom is about 10 to the minus 13th. Adrian, can you point to the nucleus of the atom? Okay, and then the electron is about 10 to the minus 15th, so can you point to that? Okay, so those are our components of an atom, but today we're talking about neutrinos, and a neutrino is much, much smaller than any part of an atom. So Adrian, can you point to where the neutrino is on our number line? It's way, way down to what's called a yoctometer, and that is 10 to the minus 24th. So you've gone down 24 powers of 10 from a meter. That is a lot. Caitlin, can you point out where a meter is? Okay, so here's a meter. Can you count down and show that it's 24 powers of 10? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. So it's much, much, much smaller than even an electron, which is the smallest part of an atom. So we're going to make a little model. So we're going to talk about first, what if we scaled up the atom so that the nucleus was the size of a grain of salt, so that you could see it. So Caitlin's going to move the nucleus up and count the number of powers of 10. She has to go, I'm sorry. Yes. Yeah. Scale the nucleus up and count the number of powers of 10 to do that. So 2, 3, 4, 5, 6, 7, 8, 9. So she's had to go up 1 billion times, or 9 powers of 10, to make the nucleus visible. So where does that take the atom? So can you move the atom up too? Yeah. It's going to go up 9 powers of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So now our atom is a meter. It's a meter in diameter, so about like that. So, and we can just barely see the nucleus. The nucleus is like a grain of salt. When we do that, where does the electron end up? Let's count 9 for that. And the neutrino. So can one of you do each and move them up? All right, so our electron is too small to see, but you could probably see it with a microscope. And our neutrino is still way too small to see. Okay, so that is one model of an atom, where the atom is a meter, and you can see the nucleus, but you still can't see the smaller components of the atom. So let's try to go another step. Let's try to take the neutrino up to look like salt. So count them, start where you are, and just count how many more orders of magnitude we have to bring up the neutrino to get it visible. 3, 4, 5, 6, 7, 8, 9, 10, 11. So now we've taken the neutrino up another 11. So where does that take the nucleus of the atom? Let's move that up 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So what's that, Adrian? 10 megameters. And in scientific notation? 10 to the 7th. So how big is our nucleus if the neutrino's the size of a grain of salt? I am going to escape out of the PowerPoint for a minute and show you a cool website which you might want to play with later. But this lets me look at things at different scales in the universe. And I am going to go up to, right there, I might an ant. So here's 1 meter to start. And then I'm going to go up to 10 to the 7th. And it's basically the size of Earth. So I'm not doing a very good job here, but we're going to put Earth on the 10 to the 7th there, because that's the size of our nucleus now. So Caitlin, can you bring up the size of the atom? So we have to go up another 11 powers of 10. 7, 8, 9, 10, 11. And where are we on that?
Oh, it is 100 gigameters.
10 to the 11th. So 100 gigameters, that's 100 billion meters, or 10 to the 11th. If we go up to there, It's actually the distance from the Earth to the sun. So think about this. If we had a neutrino the size of a grain of salt, then the atom is going to be as big as the distance from the Earth to the sun. So think about why we have to build very large detectors to see a neutrino or to detect a neutrino in our underground experiment. Oh, by the way, let me get, I did put a number line on Google Docs that if you wanted to make a copy of it and play with it and do some scaling yourself, you'd be welcome to do that. So when we are building these very large experiments underground to try to detect neutrinos, one of the reasons they're so hard to detect, even though they're the most abundant particle in the universe, they are so tiny that if you think about a neutrino the size of a grain of salt going through an atom the size goes out to the sun, what's the likelihood that it's going to hit an electron or a proton or a neutron? It's very, very low. It's mostly going to just see that atom as totally empty space. So that is why neutrinos can go right through the Earth. It can go from the sun to the Earth and through the Earth, and we never know they're there. If you hold out your thumbnail, there's 62 billion neutrinos going through your thumbnail every second, coming from the sun and going right through the Earth and keep going. So this helps explain why we need to build these very large experiments like LBNF Dune, which is coming in the future, and you'll hear about over the course of this week. Why we have to build these experiments to understand these very mysterious particles. So I think we will stop there and answer any questions. We don't have any questions. Yes. Yes. Can you?
We did have one question about whether this presentation will be available later, so if you could let people know that it will be archived on our site, they'll be able to access it later.
Okay. So there was a question about whether this presentation will be available later, and I believe that all of our live presentations over the course of this week will be archived, and so that anybody can watch them after they've happened.
Okay, we have a question. Can a neutrino be seen by a microscope?
No. An atom, oh, sorry. There was a question of whether a neutrino can be seen by a microscope. Our best microscopes can see atoms, but a neutrino is much, much too small to see with a microscope. That's why we need indirect ways to look for neutrinos. All right. Well, thank you very much for joining us, and hopefully you'll join us for the different activities we have over the course of this week, and email us with